Hi, I'm Dr. Mark Swanson, Associate Professor of Silviculture and Landscape Ecology in the School of the Environment. And today, we're going to film a segment for SOE 204, Introduction to Field Methods, that involves fixed area sampling in a forest ecosystem. In fixed area sampling, we use an area of known dimensions in which to sample trees, both the count of trees as well as other attributes like basal area, which is the cross-sectional area at breast height, 4.5 feet off the ground, to make inference up to the scale of an entire acre. And typically how this is done is with a circular plot. So we use a known radius from a sample point, for example, this flag sample point right here, and we measure every tree within a specific limiting distance. Today, we're going to do a 1/20th acre plot in which the limiting distance is 26.3 feet. So every tree within 26.3 feet of horizontal distance will be part of our sample. So that's regardless of the size of the tree, the species of the tree, or any other attribute of the tree. Now typically we start in the north and then we go clockwise. This is fairly standard for plot methodology, whether you're doing fixed area plots or what we call variable radius plots, which is another method. So to do this, we're going to use either the Spencer tape, which is a retractable forestry tape, or we could also use a laser hypsometer to determine if a tree is in the plot or outside of the plot. If the tree is in the plot, we then record the species, we record whether it's live or dead, the diameter, and then other attributes as necessary, including perhaps a subsample of height. When we use the laser hypsometer to measure whether a tree is in or out of the plot, we simply stand over the plot center stake, and we look through the device, make sure it's on the horizontal distance setting, and then we shoot it right at the tree's breast height, 4.5 feet above the ground. So for example, I'm beginning in the north, and you can see that the first tree there, tagged with blue, is going to be the tree that I'm going to shoot. So I'll shoot it, and the device returns a distance from plot center to tree edge of 34.5 feet. So we know that that tree is outside of the limiting distance of 26.3 feet. I then turn my attention to the next tree that could possibly be in the plot. It also is marked in blue. I shoot it at breast height. I'm returned a distance of 36.0 feet. So I know that that tree also is outside of the plot. I then turn to the next tree. This one is marked in orange. And again, I aim the laser at the breast height level on the tree. I shoot it, and here I'm returned a distance of 24.5 feet. I now know that the center of that tree is within that 26.3 foot radius, thus qualifying it for inclusion in the plot. If we're working without a laser hypsometer, we can use a tape like the Spencer tape to determine whether the tree is in the plot or outside of the plot. Now, where do we attach the nail, the horseshoe nail, on the Spencer tape so that we can determine whether the center of the tree is in the plot or outside of the plot? We want to go tangent to a line that extends from the plot center through the tangent edge of the tree. So we don't want to go to the face of the tree. Nope, we want to go to the tangent outside edge of the tree, right here. And then we make sure that that runs in a direct tangent line around the radius of the tree back to the plot center. So now I'm going to walk the tape, and hopefully we're on level enough ground where we can get a level tape from plot center to the tree. I walk it back, and then I look on the distance side of the Spencer tape. And here, come on in. I see that we have a distance of 25.6 feet from the edge of the tree to the plot center. We now know that this is less than the 26.3 feet that would be necessary for inclusion within the plot. So here's our limiting distance. We have our tree to plot center distance here of 25.6 feet. That distance is less than this distance, therefore that tree is inside the plot.
This is incorrect because a bent tape will overestimate the distance from the checked tree to the plot center. The correct method is shown on the right. The straightest line is chosen to run the tape from plot center to the tree being checked. This tree is clearly out because it stands at a distance of 33.8 feet from the plot center. However, it would be an in tree for a 1/10 acre plot with a radius of 37.2 feet. The tree to which this tape is attached stands at a distance of 26.36 feet from the plot center. This means that it is out because a tree must be 26.3 feet or less to be part of a 1/20th acre plot.
Once we've determined that a specific tree is inside the plot, we then go ahead and take some variables on that tree that will help us in later data analysis. One important piece of information is the species of the tree. In this case, it is a ponderosa pine. So we write down in the species column of our data sheet a code that refers to ponderosa pine. In this case, the code PP for ponderosa pine. We then assess whether the tree is live or dead. And in this case, the tree is live, it has green foliage, and so we put down an L for live, a capital L, in the column for live or dead. We then go ahead and take the diameter at breast height of the tree. This is a standard forestry measurement taken in inches or centimeters at 4.5 feet above the base of the tree on the uphill side of the tree. And we've already tied some orange flagging around this tree at breast height, so that is where we're going to take using a diameter adjusted tape here, the Spencer tape, to get that value of the actual diameter. So we stand to the uphill of the tree and we go ahead and put the tape around. We ensure that the tape is level, that we're not canting it one way or another, but that it represents a level cross-section of the stem of the tree. We then compare the circumference adjusted diameter value on this side of the tape with the 0 mark. In this case, we're getting 15.6 inches for the diameter at breast height. And that then is the value that we write down. We then convert, either back in the lab or out in the field, that diameter value in inches to what we call basal area. Imagine if we cut this tree off with a chainsaw at 4.5 feet and we measured the exposed surface area of the cross section of the stem. That value is what we call basal area. And in English forestry units, we measure that in square feet of basal area. So in this case, we have a reference card that for a given inch value gives us the basal area in square feet. We've already gone ahead and looked that up. And we get 1.31 square feet of basal area on this tree. We may then choose to go ahead and measure the height of the tree using either a clinometer or a laser hypsometer to get the overall height of the tree, in this case in feet. We're not going to do that for this laboratory exercise, but it is an important value. Overall tree height for a given age is an important indicator of the biological productivity or growth rate of the stand. Especially at the beginning of the day or early on in your forest measurements career, you want to ensure that you're accurately measuring the tree at 4.5 feet above ground level on the uphill side. So one good trick is to just use your Spencer tape, plug it in at ground level, and then using the lineal distance side of the tape, not the diameter side of the tape, you measure 4.5 feet up. So here is 4.5 feet. And then one can also compare that to something on one's cruising vest. So here for me it's at the top of the pens and pencils in my cruising vest. So that would be a good reference height for all future measurements for the day. We've now measured the distances to all adjacent trees to determine inclusion in the plot or exclusion from the plot. So starting in the north, we rotate clockwise, out tree. Here's our first in tree number 1. There's an out tree. In tree number 2. In tree number 3. That lodgepole pine in the back is out. In tree number 4. In tree number 5. And don't forget trees that might be kind of obstructed by intermediate trees. So that's tree number 6. Tree number 7. There's an out tree. Tree number 8. Out trees in the back. Tree number 9. Tree number 10. And there we had an edge tree. It was at 26.4 feet, but it just doesn't meet that criterion for inclusion of 26.3 feet. And then we return to our north angle again, and we know that we've checked all possible angles for trees for inclusion in the fixed radius plot. We now gather data on the remaining trees in the plot. Okay, what's the species, Mark? 14.8. Live. Okay, tree number 3. What species?
Ponderosa pine.
Ponderosa pine. Live. Mark's getting a good level diameter there.
This one is 17.7.
17.7.
Tree number 3.
Number 4.
Number 4. Ponderosa pine, and it's live.
Ponderosa pine. Live.
We are at 15.3.
15.3.
Tree number 5. Ponderosa pine. It is live.
Ponderosa pine. Live.
And we are at 14.7.
14.7. Okay, tree number 6.
Ponderosa pine. Live.
14.9.
Tree number 7.
Tree number 7. Ponderosa pine, live.
And it's live, and it's 19. Even.
19.0. You always want to record it to the 10th, either centimeters or inches.
Tree number 8.
Okay, tree number 8.
Ponderosa pine.
Ponderosa pine,
Still live.
live.
And this one is 12.6.
12.6.
Tree number 9.
Tree number 9.
Ponderosa pine. Live.
14.9.
And our last tree.
Last tree.
Ponderosa pine. Live.
Ponderosa pine, live.
And we are at 12.4.
12.4. All right, perfect. Thanks, Mark.
Yep.
So here's our completed data sheet. We've listed who the observers are, Mark Swanson, Mark Batchelor. We've listed the date. We've listed our plot size in acres, in this case 1/20th. And that's very important because of how we're going to expand our numbers to the level of an acre later on. We also write down the radius of the plot, 26.3 feet. And that helps us in our field sampling because that now becomes a value that is much harder to forget. Our slope is 15%. Our aspect, which we obtained with a compass, is 5 degrees, so almost due north. And our elevation, which in this case we derived from a GPS unit, is 2,503 feet above mean sea level. We then have our plot data, trees 1 through 10. We have a species value for each tree, we have a live or dead value for each tree. We've got a diameter or breast height in inches for each tree. We could even specify that this is in inches. We have a basal area that was tabulated from the diameter data, and we have these values for all of the trees. So, what can we now do with this? Let's look at a couple of summary statistics. First off, how many trees per acre do we have? This is a quantity that foresters call the density, and it's simply the count of trees per unit area, in our case, to the acre. Now we know that the plot was 1/20th of an acre. So to take these values and expand them to the level of an acre, we take the inverse of the 1/20th value of the plot. So 1 over 20 is equal to 20. This is the number that we use to multiply anything that we quantify within the plot to expand it to the level of the acre. So this is what we call our expansion factor. And it's the number by which we multiply anything we measure to expand that number to the level of the acre. Let's look at an example. We had 10 trees in the plot. We multiply those 10 trees by our expansion factor of 20 to get to an estimate of density at the level of the acre. So our point estimate from this plot of trees per acre is 200. Alright, next we can do some categorical data. What's our modal tree species? In other words, the most common tree species? It's ponderosa pine, because all of the trees in this plot were ponderosa pine. What was our modal condition for those trees? Because this is a relatively healthy stand, they were all living, and so the modal condition was live. Now let's look at basal area. We have a basal area value for each tree. To get to the level of basal area for the plot, we simply sum those values. So the sum of all these basal area values of square feet per tree was 10.91. Now how do we expand that to the acre? Again, we take the summed basal area, we multiply times 20, and that gives us our basal area per acre estimate of 218.2 square feet per acre. And that's a very important value for foresters because we can use this to calculate volume. We can use it to estimate the stocking, how crowded these trees are relative to other areas of the forest, and do many other things. Basal area is a very important quantity when we're trying to quantify either forest production or habitat values if we're working in wildlife. Now we just did one plot in today's exercise, but in actual resource management, we would want to take a number of plots distributed throughout a stand in order to characterize the nature of that stand. So this brings us into the field of sampling. And typically in forest and habitat habitat measurement activities, you want to have a number of samples throughout the stand, often on a square or rectangular grid, just like this, plot 1, plot 2, 3, 4, all the way up through plot 12. And you would put in one of these plots at each of those points. Often you do this in collaboration with a GPS unit to guide you to those plot centers throughout that overall stand area. Then, any statistics that are calculated at the level of each plot are going to be summed with the other statistics so that we get an idea of the average and then variation around the average of those plots. With a lot of compasses, we have the declination scale, which helps us adjust magnetic north as opposed to true north. But if there's a weighted needle, there's a little black weighted needle in the bezel of the compass that when we turn the compass east to west, we can now turn the compass alongside the slope like so, and that little weighted needle will tell us the slope of the actual topography in degrees. This can help us decide if we're at a steep enough slope where we might need to make slope corrections because the distances from plot center to the tree are going to be influenced by slope. Now if we're using the laser hypsometer and the horizontal distance setting on the laser hypsometer, then that is taken care of. But if we're using traditional equipment like dispenser tape, then we need to adjust for slope. Now you can do that in the field using a hand calculator and doing the trigonometry to calculate the actual horizontal distance, or you can just do slope distance measurements to each of the trees and then correct the actual area of the plot in the office later on. Now, how do we know where to put these plot centers? Well, we can use a paper map like I have here and then use pacing and a compass in order to find the plot centers, or we can use a GPS that has been preloaded with coordinates for each of the plot centers. Once we locate our plot center, we typically put a stick or a pin flag in the ground that has flagging so that others might find the same plot center if they need to check our work or for whatever other reason relocate that particular plot. So this can be either a permanent feature that we leave behind in the field, or it's flagging that we can pick up at the end of the day and then move on. Now, if this is a permanent sample plot in which forest scientists or forest managers track forest growth and mortality and other dynamic processes over long periods of time, this would be a much more heavily monumented center with something like rebar with a very colorful rebar cap for safety and for ease of relocation. So there are a lot of ways that we can mark out the plot center, but flagging tied onto a stick with critical data like the date, the initials of the timber measurement person, the plot number, and maybe the size of the plot, all critical things to mark onto the flagging with a Sharpie pen. That way, if the plot needs to be relocated and the data remeasured, then the person coming to do that will have all the data that they need. Now for this video demonstration, we put orange cruisers flagging around each of the trees. This you would not do in an actual timber inventory action. What you might do is use some marking paint to put a dot on each tree to indicate that you've already measured it, that it's already been included in the sample. Now in today's exercise, we used a good old piece of paper on an old-fashioned forestry clipboard. You'll often hear them referred to as a Tatum. But increasingly commonly, both in forest management and in forest science, we use digital data loggers like iPads or Android-based devices or PC operating system-based devices that have data collection software on them. So it's possible that you could enter data for a plot and immediately calculate summary statistics for that plot. And then at the end of the field day, you could collate the data from a number of different plots and have fairly immediate results of your forest inventory work. Well, everyone, it's been a great time doing this. I hope that you learned something about how we measure forest habitats and the forest resource itself. Thanks again, and take care. We'll talk to you soon.